In this video, I'm going to walk through getting my SD card reader working. Now in the last video, I used this versatile interface adapter to connect to a real-time clock through SPI, and that all turned out fine. Now in this video, I'm going to take the same versatile interface adapter, or VIA, and connect through SPI, the same SPI bus, over to this SD card reader. I did note in the last video that this SD card reader is a poor design, and it does not basically put the MISO into a tri-state. So when it is not enabled, when the chip select is not active, it's still outputting to this master in slave out line, which will cause issues with any other devices using that same line. So I did have to split that out. So the MISO from this device is going to a dedicated pin on the port of the versatile interface adapter, different from the MISO line for the real-time clock. The two devices share the same MOSI, which is a master out slave in. So going from the VIA or from my microcontroller out to the two SPI devices, and they also have a shared clock, a shift clock for the SPI. But they have their own special MISO lines connected to the VIA. Not a big deal. I had spare lines there that I could use for that. I still have two ports I can use, and I don't know if I should call them ports, but SPI headers that I can use with appropriate chip selects, that I could add two more SPI devices and still control it all with a single port on this versatile interface adapter. Now, as I work with these two devices, the low-level bit banging to do SPI is essentially the same. There's one minor difference. The real-time clock was using SPI mode 1, and this SD card is using SPI mode 0. Now, the difference is at what point is data valid as it's being shifted, and it goes off of the shift clock, and either the clock on a rise or on a fall. And there's a difference between SPI mode 0 and 1 as far as where on the rise or the fall, and what is the idle state. Is the clock high on idle or low on idle? But there's a minor difference there. So if I go through this, or you look at the code later, the bit banging, that's really the only difference is when the data is valid as it's being shifted based on the clock. Now to work with this SD card, I need the low-level SPI, write a byte, read a byte type of thing. But I also need to work with all the different SD card commands. And here on the screen, what you're seeing is a list of some of the commands that I've set up in my code so far. So these SD card commands really are a 6-byte packet. So there's 6 bytes of data you need to send over to the SD card. First of all, there's a byte that says which specific command. Then there are 4 bytes for arguments if that specific command takes or requires arguments. Otherwise, you just can send zeros. And then there's a CRC, or a checksum. And I did note down below, 2 of these really you really should have the CRC on it, and that is command 0 and command 8. So when I send those commands, I need a specific CRC that's been calculated. And I don't try to calculate that on the fly. I know what the CRC is for command 0 and command 8, and I'll hard code those. The rest of these do not take CRCs unless you run a different command to enable more CRC requirements. But for what I'm doing, only CMD 0 and 8 does the CRC really matter. And if I look through this command list, I've got command 0 down to command 55. The command 0 is basically a reset. Command 8 is just a check to see, does this SD card handle this SDHC. Basically, I think it's just checking for a certain voltage level support. Command 12 is to stop reading if you started a multiple, which is a command 18. So I can say I want to read multiple blocks, and when I'm done reading, I basically send back a stop transmission at command 12. Command 13 just gives me the status of the SD card. Command 17, which I'm going to use quite a bit here, is read single block. So read one block. And I know it says read single block here, but I'm also referred to, I think, as a sector. And I see terminology go back and forth here, but And a lot of the constants it's set up as a read single block, but documentation wise, it's really a sector. And those are 512 bytes in size. Then there is also a write block. So I want to write 512 bytes to the SD card. That's a command 24. And then there's this command 55 that notes I want to use an application specific command, and you'll follow it then with an application specific command, like in my case, 41. So that's I noted it as an ACMD 41. So it's an application specific command 41. And that's essentially to do an initialization or init the card. And basically make it usable at that point, turn it on, not writing to the card anything, but just basically saying, okay, initialize access to the card. I did note here 3 of these commands, 17, 18, and 24, do have parameter data that you need to specify, which is logical block addressing, or LBA. It's just a way of addressing space on the SD card in a linear fashion. So you need to tell it which specific sector are you trying to read or write. And that is a parameter that has to be filled in, then those 4 bytes before you make the SPI call using command 17, 18, or 24. So those are some of the commands I'm going to be using. Now, if I look at the actual overview of code here that I'll be going through, I'll just pull that up. This is what I'm doing to get to this first stage of SD card access, I guess. I have more work later, but I'm going to start with this. I've written a routine called test SD card full. And in it, it does an SD card init. It calls basically a routine that does an initialization. And in it, I do a command 0, which is a reset, then a command 8 to check for this SDHC support. Then a command 55 followed by the 41, which is basically go ahead and init this card, get it online so I can start using it. After that, I am setting this logical block addressing and basically saying where on the card do I want to read or write. So in the future, as I am using FAT16, hopefully in a later video, that's going to help me understand, well, where should I be writing a file and where do I read a file based on the FAT16 information. But I'll have to set an address. Where on the card do I want to do something? And in my case, I want to do a test write. I want to write a sector of data, and then I want to turn around and read it back and make sure that it worked. So in this case, I will set an address, and you'll see that in my code when I get to that. And then there is a test fill loop. So I have a buffer in RAM, just called SD card _ buffer _ PTR. But in that, I'm going to fill in, this 512 bytes of data that I want to write to the card. So I want to have it prepared in RAM first, and I'm going to just, create a little sequence of test values, starting out with like a 0 and then a 1 and 2 and 3, and I'll just work my way up and write out those bytes. And then I'll turn around and take that buffer that's in RAM and write it to the actual sector on the card with this CMD24. Now, as part of that, it will call a routine I wrote called prep RAM command, and that basically will inject the LBA, so what address do I actually want to read or write, into the command sequence. So it's going to say, here's a command 24. Here are the 4 bytes to specify which specific sector I'm trying to read or write, along with a checksum, which I don't actually use on this command 24. Then I clear the RAM where I had stored that buffer that I was going to write, because it should be out on the card at this point. I can clear the buffer. I then turn around and read back from the SD card into that buffer. So I've done a write to a buffer. I wrote the buffer over to the SD card. I cleared the buffer, and now I'm going to read back from the card into that buffer. And then I just test, and I only look for now at the first 16 bytes. Basically, if that works, the rest is going to be fine. But I check 16 bytes just to make sure it matches the test pattern that I had expected to have been written to the card and read back from the card. Now, I'll show you what the result of this is, and it's not very maybe exciting, but then I'll walk through the code in a second. And I will maybe do a couple of things here. So on my board, I'm going to go ahead and power it down, take out this SD card, and maybe pop it into a reader. And so then when this comes up, it pulls up that I've got this drive G, which I am going to format. Okay, and right now this is a 60 gig or 64 gig card. It shows up here as capacity of 58.2 gig. That's fine. Later I will actually partition this, and I intend to only use maybe 500 meg partitions or a 500 meg partition just to keep the FAT basically table really small and have that cache in memory. And 500 meg is going to be way more than I'm ever going to need on this system. But for now, I'm not doing any partitioning. One partition, one really big partition, and I will go ahead and erase this. So I now have this, and I'm going to open up a piece of software here called HXD, and I'm going to open up that disk that I just formatted. And here is the removable disk I'm using. So I'm going to open up this in read-only and just look at what's on the disk after I format it. And so when I look at this, first of all, this is showing me the sectors, and then I can see what's in each of these sectors. And so I can see it wrote out something in here that says, okay, this is using whatever XFAT and a bunch of data. You know, I don't know what all this metadata is. I'm not even worried about what this metadata is. But then I can read through and I can see there's a bunch of information. You know, this is probably a FAT type of information. Up through sector 2, and then it looks like at sector 3 on, it is zeros. So the rest of this card is zeroed out, and it looks like to a certain point, and then it flips to Fs. Oh, it looks like there's something at sector 11, 12. Now, when I do just a quick format, it doesn't actually go through and zero out the card. It really just zeroes out the table that says what's on the card. So according to FAT, this is all empty, but I can see there's some remnants of stuff out here. I am going to go back though, because I think I'm going to write to sector 16 as we get in here, and I just want to see if there's anything in here right now. So sector 16 is a bunch of zeros, looks like a little bit of garbage here at the end. Maybe some previous testing of a 55AA that was being done. But that's what this card looks like right now. And again, sector 16, I'm noticing, looks like this. So I'm going to go ahead and close this, and then I'm going to eject the disk on my other screen and take this SD card and put it into my system. And then I will fire things up. Now, as I fire that up, I'm going to pull up my serial output, and then I'm also going to pull up the VGA capture just so we have that up here. Okay, I'm going to reset this one quick time. Okay, I had to reset my Terra term. It was acting a little goofy there. But my system's booted up, and what you can see now here is I've added a new command called SD or test SD card. So I'm going to go ahead and run that test SD card. And on my main VGA output, I don't do anything, but on the debugging output to my serial, I wrote out a bunch of things. And first of all, I do this open curly brace in a 00 saying, okay, I'm starting the initialization. And 00 is saying I'm sending a command 0, then I sent a command 8, then I sent a 55 followed by a 41. So the 55, 41 was the app specific, and then a init. And sometimes that takes a little bit for the card. You have to wait for the card to finish initialization. So I try the init, I give it a little bit of a delay, and then I try it again. And I keep trying it until the card comes back with a response that says, yep, I'm good to go. And then I've got some garbage that is just debug output that will mean something to me, but I basically say a dot when I'm done with the initialization. So at that point, the card is active. I say that I'm going to do a write. After I get done writing, I clear the temporary memory. I put a little X there for that. Then I'm going to do a read, and then I'm going to do a verify. And if everything works, I put up a $sign. And if it doesn't work, I put up an exclamation or a large X, a capital X, depending on what was going on. Now, obviously, I could be more verbose on that output, but this is just temporary testing to let me see, did the card initialize? Did it do a sequence of things? And did I get to the $sign at the end of the day? That's what I'm looking for. And it shows that it did. So I'm going to turn the system off and put this card back into my PC. And just also go kind of look at it from this perspective and see what does that look like. So let me get back over here and I will open up that disk again, removable disk. And I'm going to go down, and I believe my code was at sector 10. So that's, or not 10, sector 16. And there is the test that I wrote out. And so basically what I've written out is just a test pattern, a 0, a 0, 0, 0, 1, 2, 3, 4. You can see I count up, and then I get to 9, and I go to 0A. I continue counting, and then I get to 1s, 2s, 3s. So you can see I'm counting all the way up through FF, and then I just repeat it again. So I go back from 0, 0 all the way up to FF. And over to the right, it's trying to interpret that as ASCII, and that's fine, and it does that for some of that. But these were just raw bytes that I wrote, starting with 0, 0, going to FF, and then repeating that. And so I know it wrote to that. I also know that it read it back and tested it correctly because I ended up with this $sign over here. So that was the result I was looking for. Now let me go through the code that I have that helped me do that. So first of all, in my main project, just as a reminder, I have a project for my primary board, which this bottom board is the primary board there. And I have this SPI. And in the last video, I was using this file for my real-time clock work. I've defined the pins on my versatile interface adapter. Again, I had mentioned this MISO on the SD card is on a separate pin versus the MISO for everything else. And then I've got a MOSI serial clock or shift clock, and then I've got a couple of chip selects that are open and a couple of chip selects that I'm using, one for the real-time clock and one for the SD card. And I do have a little summary here on the SPI modes. So again, my SD card is mode 0. So that just tells me that on the rising clock, when the clock goes low to high, is when I should be reading data. And I've added a section down here called COP interface. And for those following on my video series here, the way that I'm accessing or trying to expose functionality on this primary board in its operating system is essentially through this coprocessor instruction of the 65816. And so I'm setting these routines up so that I can expose them through a COP call. And so that later when I do some C coding for FAT16, when I want to access the SD card, I'll just do some simple COP calls. And really the things that I'm going to expose are this SD card init, and then also the read sector and the write sector. And that's probably it. These others will be supporting things behind the scenes like set LBA. So I'll be able to say initialize the card, and then I can say read a sector, and I can tell it the LBA as part of the parameter for that coming from C. And then within this, or within the COP routine, I'll do a set LBA followed by a read sector. And then the data that I read will go into RAM that the C code can access. I've got some unused stuff down here, and I have a whole bunch of other supporting routines up here that were either for the real-time clock or some of these that are used just for the SD card in general. So supporting routines like sending certain command sequences. But the main routines that I'm going to go through are right down here. Now in this case, for this video, I'm just using this test SD card full. So all the testing that it went through was going through this here. And you can see there's a block of code that's decent sized. But let me just kind of talk through that a little bit. First things first, I am setting up a location in memory just to store a buffer. So where's my data going to go that I want to write to the SD card? I first have to prepare it in RAM, or when I read it back, I want to put it back into a buffer. So I have a buffer that I've set up at 1200 for the address, so hex 1200, and that I picked just arbitrarily. I picked a spot that I didn't think was being used. And then I call an init. And so I have an SD card init routine that I can go look at. And if I look at the init, basically I'm going to go through this really quickly here. I print out some debug output. There was that open curly brace you saw in my output. I have to bring the chip select. Basically, I bring it to a normal idle state. I bring my clock low, and then later you're going to see that I'm going to modify this chip select on the specific SD card. So I get in here then, and I have a clock pulse, so I go ahead and flip the clock, and I'll kind of keep working through this. But what I have to be able to do is, first of all, this command 0. So if I go back to my slides for a second, and I back up a slide. So command 0 was my reset, followed by this check for SDHC. And then in my code, here I am doing that, basically saying, okay, go out and find this command structure that I have set up called cmd0_bytes. Now in my, the way I've done this is in my code here, I have all of the command sequences set up here. So here's cmd0bytes. It's a command hex 40. It has no parameter data. And then it has a signature, a CRC of 95. So that's the first thing I'm going to send is that set of 6 bytes that is a command 0. And so when I do an init, I say, go load up those 6 bytes. So basically point to that location where that's at. Store that as my address that it's going to use to process those bytes. And then I have a procedure called send command. And so that send command is up higher. But then that goes through and says, okay, read out those 6 bytes and then go ahead and send those to the SD card as a write byte. So I've got a write byte and I have a read byte. Now some people will put the write and read as a single common routine because basically as you write, it's reading simultaneously. So you could do 2 writes and the second one will actually bring you back what the result was. It's the same as a read. For me, I just like I like to see it as a write byte, and then I have a later procedure called a read byte. But this is writing out my command, my 4 pieces of argument information or data that goes with it, and a CRC. And so this is just what this routine does, and then it turns back and reads back a byte. So it sends the byte and then reads back basically with this SPI SD card read byte. And that's just putting in 8 extra clocks for the card to finish doing what it was doing up here. So I've got this send command. I've got other commands here in this list that I'll have to go through. So I come in and I do a 0. I'm expecting that after I send command 0, that second byte, remember I write a byte, that's command 0, and then I'm reading, well, I'm sending all of the 6 bytes for the command, but then I'm reading back 1 byte, and that 1 byte I should read back as a 1. The SD card should send me a 1 saying, yep, I'm not initialized. So I've gone into this reset state. I'm in a non-initialized state. I then turn around and say, okay, if that did not work, try it again. And I haven't seen that doesn't work the first time on this setup. So then it just is going to continue and fall into cop try 8. And so this try 8 is going to try to send command 8. And again, if I go back over here, command 8 then is, does the card support this SDHC? And at the end of that, I'm expecting a 1. And if it's a 1, then I'm going to move on. And I do need to read back. It sends back some data. I basically flush that with 4 reads, and I get that out of there. I then do a 55 and a 41. So this is an app-specific command. And then an init is essentially what the 41 is. And now, again, when I do that, it might not instantly come back as ready. So I'm expecting it to eventually come back with a status of 00 saying it's initialized. But if it doesn't right away, that's fine. Then I just jump back up and I try it again. So I come up here and I say, well, okay, let's try to send the 41 again. But you have to say, here's my app specific command 55, which is a 41, is the actual command. So 55, 41, you'll do those in pairs. And every time I do that, I check it. If it's not what I'm looking for, I come back up. I delay 10 milliseconds approximately try it again. And you can see on the output that it does take a little bit of time. And depending on which card I have plugged in, I have a series of different SD cards here. This will take longer. So in some cases, I'll see more of these work down the screen, maybe twice as many, 3 times as many on some of the cards that don't run as fast. But in this case, I tried it. It wasn't ready. I tried it. I tried it. I tried it. And finally, it was ready. So 1, 2, 3, 4, 5. It took five rounds of this try 55, followed by a try 41 before the card said, "Yep, I'm ready." So then at that point, I put a dot out on the serial screen, and there you can see the dot right down here, just saying, okay, initialization is done. The card is online, ready to go. And then in my testing, after I do the initialization, I then set where do I want to write to. And so for my testing in this video, what I just did is I said, use a hex 10, which is a decimal 16. And that's saying I want to use sector 16 for my read or write, whatever I'm going to do next. But that's where I want to do it at. I have also done testing with very higher LBA within the SD card, so more towards the 60 gig location. So here was a case where I set the low and the high bytes, so it's 4 bytes that are letting me set that LBA to a 60 gig address roughly, just to do the testing, and same result. But for this one, just so it's easy to scroll to inside of that other utility over here, I put it down somewhere lower, like sector 16 or hex 10 for the sector, so I could see it without scrolling way down or having to jump down. So then once I say that's the location I want to work in, I call a set LBA, and all it does is it stores that in memory. It just says, remember this location as where we're going to work. Then I fill up this buffer. And basically what I want to do with the buffer is just run through a loop and put in values. Start with a 0, go to a 1, 2, 3, 4, basically work its way up. And that's all this is doing. So I start with a 0 and then I increment my way up as I go through this. So then that is going to go ahead and basically fill some test data into that buffer in RAM. Then I want to write to it, so I put out a W to the screen that you see over here. That W is just saying, okay, now I'm going to go ahead and write to the SD card. And what I'm going to try to do is say write an entire sector. So I have this routine of SD card write sector, and in it, basically, I'm going to come in here and send a command 24. Now the command 24, if I come over here, is a write block. So I want to write a block, which is 512 bytes. And this is basically coming in here and saying, start this command of a 24. And in that, I do have a separate routine it calls that basically loads up the command 24 bytes. Again, it's got to go grab me the right command number, the parameter data, the CRC. Really all that matters is the command number in this case. Gets that loaded up. And then I have a routine called prep RAM command. And what this does is the injecting. So it takes the, what I'm saying I want to use for an LBA address, which was stored in this SD LBA, and injects that into the 4 bytes of parameter data. All this is doing is getting my command number followed by my 4 bytes of LBA addressing put in, so that when I do call the 24, it calls it properly with the location of where I want to do that write. So that's all done through those routines. And then I come in here and I can start writing data. You have to write a dummy byte followed by a send data start token, which is an FE. And then I just simply have a loop that's going to run through and start pulling data from my buffer and writing it to the SD card. And so you can see here what that process looks like if you want to look at that in more detail. But it's basically some CRC information, and lots of writing bytes. And that gets me through this writing out a sector. So then after I write out a sector, let me come back up here, then I should be able to get to this point where I write out to the serial a small x, and I have a loop that just simply clears that buffer and RAM. So I had filled the buffer with a test pattern. Now I'm going to erase that buffer, because I'm going to then follow it by a read, and I'm going to read a sector, very similar to my write sector. It uses the appropriate command to do a read sector. It goes to the SD card, reads that 512 bytes, and puts it into the buffer that I was using up here. And then at the end of that, I've done the read, and then I move into here, and I'm going to have to do a verify. And so I have a loop that goes through and looks at the first 16 bytes and checks to see, does this buffer contain, the 16 bytes that I'm looking for. And if it does, I print out a $sign. And if it doesn't, I can either mark a data mismatch. I can also show that the test overall fails. Now, when I look at my output here, I can see that I had my read, my verify, and then a $sign. And that $sign is only showing up if I was successful. So that is basically what this is going through, is doing all of that. And that is part of my test routine. So just to kind of walk through that again real quickly, I set my LBA, what address do I want to work with. I fill up some test data, I write the data, I clear the data in RAM, I read back the data, and then I just verify the first 16 bytes match the pattern that I was expecting. And then you saw me pull the card, bring it over into this other software, and see what actually was written to the card. And I can validate it was put into the correct sector, and it matches the pattern for the full sector that I was expecting. So that is a way that I can validate that. So that's this test card full. Now that is just a temporary routine just to do this testing here, and it gives me some confidence that my init is working, the set LBA is working, the write and the read sectors are all working. So what I'll be able to do next is set up an interface through COP so that I can write a C application that will leverage these three calls: do an init, tell it that I want to read a sector, and as parameter data, tell it which specific sector I want to read, and I could probably even give it a pointer to where it should read it into RAM. And then the write will be the same thing. I want to write from where in RAM do I want to write to which specific address on the SD card for LBA do I want to use. And these routines should be simple COP calls that let me do that. And then my goal then is that I'm going to use a C application that does all of the FAT16 work. I could implement that in assembly. I think it's going to be a lot easier if I do it in C. So that is the path that I'm going to go down, is I'm going to write all of that in C. And I think I'm going to actually start building a command interpreter in C. Maybe it's kind of like how DOS does it, Microsoft DOS, but basically I'll have my system boot. It'll boot to all the assembly on my call it my core flash ROM over here. But then the first thing it's going to load when it gets done with that is a C application that is my command interpreter. And then that command interpreter will give me FAT16 support. It'll give me support to load up other C applications, to do anything else I want to do as part of my lowest level operating system type of functionality. So that's the path I'm headed down, and we'll see how that turns out. But the next step for me now is to get into C and try to get a FAT16 implementation working, leveraging COP calls to these three highlighted routines right here. And if that all works, then that's really going to open the door that I can create a whole bunch of different C applications, put them on the SD card, and then have my main command interpreter be able to do a directory of that SD card. And then I can run applications off the SD card. I can read data files. I can write back data files to the SD card, etc. So I think I'm making pretty good progress there, but that will be the next set of work that I need to go through. I will get this code posted as I usually do. You can read through. I have all these different commands up here. If you want to see, how does my real-time clock write byte compare to like the SD card write byte, you can see that there's minor differences in that. Again, it had to do with the rising or falling edge of the clock when the data is valid. I do have some routines down here, like a unified SD card transfer that does both the write and the read. So I can just, anytime I need to do a transfer, whether it's a write or a read, I could just say transfer. So if I had to do a write followed by a read, I'd do a transfer. Just a different way of doing it. I'm not using it. There's also a get status here that I'm not using yet, but that goes out and does a command 13 just to ask the card, hey, what's your status? And then this looks like it's only reading 1 byte back, but I think the status actually provides 2 bytes. So I probably should have a pair of reads here. And I'm just going to put this in here as a reminder to look at that later. Let's see if there's anything else noteworthy up here. Probably not. You will see that when I do send command, I've got 2 versions. One of these within the send command does do toggling of my chip select. So here's a toggle of the chip select beginning and end. And then I have a version that does not toggle. So any of these commands where you're going to say, I want to read a bunch of bytes to follow, you don't want to disable the card as soon as you send the command. You send the command, you got to leave it enabled, read back your 512 bytes of data as an example, then you want to disable it if you're done with it. So I have 2 versions, one of these that does toggle the chip select, the other one that does not. So in this video, the work that I'm doing to read and write 512 bytes is leveraging this no chip select toggle version of the send command. And I imagine I'll continue to improve this and optimize this as I move forward, but this is how it's set up right now. Okay, so that's it. At this point then, I have an SD card that I can initialize, I can write to it, I can read from it, and I can validate that it is doing all of that, writing to the location that I expect it to with the correct information. And that sets the stage now for FAT16 coming from a C application as part of an operating system command interpreter that I'll start working on next.